Hello, welcome to our lecture on the one sample z-test. It's very important that you understand when to use this test. Now, you have a sample mean of data that you've collected, and you want to compare this sample mean to a known population mean. And you must have the known population standard deviation. Before we can even start the process, we have to check for outliers in our data set. So we're going to run the MAD outlier detector. We're going to check for impossible values, particularly in our own research. I'm not going to put impossible values in problems anymore, so you don't have to worry about it. It's just not fun, so you don't have to worry about that. But if you want to check for normality and transform your data set as a result for your own personal data, this is something I will help you with. After we clean our data, our next step is to state our null hypothesis in two specific ways. The first way is in a way that anyone can understand, and then the second way is a mean difference. So in today's example, I'm pretending that I created this SAT course for local high school students. I'm curious as a teacher and a scientist whether or not my course helps these students. I hope it does, but it might harm these students' SAT scores. So I want to know that as well so I can stop the program if it doesn't exist or if it doesn't work. So my null hypothesis is that my program doesn't work compared to the known national average on SAT scores of 1059. So, my null hypothesis is just that my program doesn't work and it doesn't improve or worsen SAT scores any more than the known population average of 1059. When I want to state this, I have a little phrase here. I am trying to statistically disprove the idea that the true population mean on SAT scores for all individuals who take my SAT prep course is the same as the known population SAT score average of 1059 that has been calculated in the past for all test takers or from all test takers. When I'm stating it has a mean difference, I'm saying I am trying to statistically disprove the idea that the true population mean of the SAT scores for all people after they take my course minus the true population mean of SAT scores for all SAT test takers who did not take my course equals 0. I did not include 1059 in that null hypothesis directly. I threw it in there just so I can keep track of it, right? Like we know that's the known population mean, but ultimately what's important here is that I am suggesting that my mean difference is 0. I honestly don't care how you state it. What I really want is I want one statement that, your experiment didn't work, someone else's experiment didn't work. In this case, it's my SAT course prep. My SAT course didn't work. That's my null hypothesis. But it didn't work in comparison to the known population mean of 1059, right? And that's just really, really important. We need to realize that science works through disproof, and it is this null hypothesis that we are trying to disprove. We are trying to disprove the hypothesis that the true population mean of everyone who takes my SAT course minus the true population mean of everyone who does not take my SAT course equals 0. I want to disprove that there is no difference between my course and anyone who does not take my course. You can word this a lot of different ways. Sometimes I struggle with wording at times, but ultimately I put in there, we are trying to statistically disprove the idea because this is where disproof in science happens, through our statistics, and we're trying to disprove the null hypothesis, the idea that these two population means are identical. And yes, I only know one population mean. The other population mean I am inferring from my sample statistics. So this is where the inferential statistics comes from. Anything with a p-value is inferring a true population value. In this case, it's means. Yes, I only have a sample of students in my course, but from that sample, I'm going to extrapolate a population mean, a predicted population mean value. My second step is to gather all my known population values and simple descriptive statistics. We already know how to do this. We've already spent days doing this. My mean of my sample is 1050. My standard deviation of my sample, these are SAT scores, is 400. My known mean of the comparison population, this is all people who take the SAT scores, is a mu of 1059. The known standard deviation of the comparison population is my sigma of 210. My mean difference, which is the thing I really care about, is 1050 minus 1059. That's a -9. The negative, your sample mean is smaller than your known population mean. Positive, your sample mean is larger. Ultimately, you can take the absolute value here, but I'm just pointing out that it's important to know, and we can take this by just looking here and seeing these two numbers, that my 1050 is 9 SAT scores smaller than the known population score of 1059. So I also need to know my N, my number of participants, and there were just 9 in my course. This will be a known value, or you'll see it in your data set, okay? So step number 2, I need to know where I stand, right? I want to know what my mean difference is, because that's what I'm going to use to disprove the null hypothesis. The other stuff, it's nice to have those handy. If I'm using a sheet of paper, this is going to be the most important piece of paper, part of the paper where I can do my calculations. Our third step is to calculate and interpret our Cohen's d. Now for a one sample z-test, the Cohen's d equals the sample mean minus the population mean divided by the population standard deviation. In this example, that is just simply 1050 minus 1059 divided by 210. That is 9 divided by 210, and that is 0.04. So I know that my sample mean of 1050 is just a tiny, minuscule 0.04 standard deviations less than the known population mean of 1059. Additionally, all Cohen's d's are simply a signal to noise ratio. Signal's the mean difference, noise is the standard deviation. So when we look at that, our signal is 0.04 times the size of our noise. This is a small effect according to Cohen's interpretation rules, where 0.2 is considered a small effect, 0.5 is considered a medium effect, and 0.8 or above is considered large. Now, in general, most people interpret these as going above for the most part. Anything less than 0.2 is low, right? Anything less than 0.2 is really low. Anything between 0.2 and 0.5 is really low to medium. It just depends on where it falls. Anything between 0.5 and 0.8 is considered medium or medium to large, and then large is 0.8 or above. So we use these rules that were given to us by Jacob Cohen, the inventor of Cohen's d. So we do this because it tells us something different than our p-value. you can have a significant p-value that is relatively meaningless when you look at the Cohen's d. Almost the tiniest effect ever like this. So this study finds significance. We know not to trust it already just by calculating our Cohen's d. So our fourth step is to create our visual representation of, first, the random sampling distribution of mean differences if the null hypothesis were true, and the visual representation of the p-value problem we're trying to solve. And essentially, the p-value problem is just the probability of sampling a mean difference as extreme or more extreme than the mean difference we sampled if the null hypothesis were true. So the random sampling distribution of mean differences is a distribution of all possible mean differences that we could sample if the null hypothesis were true and there was no effect. In this case, the SAT program I created is no more effective, has no impact on SAT scores in comparison to the known population mean SAT score. Now, this random sampling distribution of mean differences has a normal shape. We talked about this before. The limits are negative infinity to positive infinity. The standard deviation has a special name. It's called standard error. In this case, the symbol for standard error in a one-sample z-test is sigma e standard error, and that equals our known population mean, sigma, divided by the square root of n. This equals 210 divided by the square root of 9. That equals 210 divided by 3. That equals 70. This step is important because we are trying to disprove the null hypothesis. By drawing it out, we can see what we're trying to disprove and the probability of sampling any mean from negative infinity to positive infinity if the null hypothesis were true. The real trick here is to realize that if the probability of sampling a mean difference as extreme or more extreme than the mean difference we sampled if the null were true is really small, we say that we've disproven the null hypothesis. But for me, this step is all about knowing what you're doing. Most people that calculate a p-value, unless they're statisticians, really don't understand what they're trying to do with that p-value. They're really trying to say, hey, the probability of sampling a mean difference as extreme as the mean difference I sampled, if the null were true, is really, really, really low, and thus I am going to say I have statistically disproven the null hypothesis. You need to be able to see that, and you need to be able to figure out, hey, where is my p-value coming from? What is it exactly? So I need you to know exactly what you're doing. That's why this step is important. So our standard error is the standard deviation in our random sampling distribution of mean differences. As your standard error or standard deviation increases, the normal curve gets flatter and flatter and flatter. That's important to know. I make you put the standard error on your random sampling distribution of mean differences because it's important, and it's important because that standard error determines how flat or how peaked your normal curve is. Now, I'm not asking you to change how you draw your normal curve. That's just too difficult. I just want you to know, oh, when my standard error is 70, I have a very flat normal curve. All of these are normal curves. As the standard deviation increases, your normal curve gets flatter and flatter and flatter. In addition to drawing a random sampling distribution of the mean difference when the null is true, we also want to have a visual representation of our p-value that we're trying to calculate. Now, essentially, we know from previously that the shape of our distribution is normal, our limits are negative infinity to positive infinity, and the standard deviation is standard error. Now, to understand our p-value, we have to add our mean difference to this picture. We have to also add the mirror image of our mean difference to this picture because all tests we run are two-tailed. And finally, we just shade in the entire area we are trying to solve for. Pretty much all your random sampling distributions of mean difference will look nearly identical to this. They are shaped like a normal curve. It's a bell, right? Bell-shaped pizza. We remember that. The limits are negative infinity to positive infinity. The most commonly sampled mean difference, the height of the hump, is a mean difference of 0 because remember, if the null is true, there is no mean difference to be observed. Then we place our sampled mean difference on the curve. In this case, it's -9, so it goes on the left side, right? And I got an arrow pointing to it. And then we put our mirror image of our sampled mean difference on the curve. That's +9. And then I have these two arrows saying that this shaded area is half our p-value and this shaded area is half our p-value. You do not have to adjust the size of your normal curve to fit the standard error. I didn't draw a very flat normal curve here. I just want you to know that that's what standard error means. So we put it up there so that we can say, oh yeah, based on that previous picture, this would be a very flat curve, but I just need that on there. And essentially I can see, oh, I'm trying to solve for the sum of those two gray areas. But this is the answer that I want. Now, step 5, we call it calculating the test statistics, right? In this case, we're calculating our z-score. Now, first, let's just talk about the statistic. A z-score equals the known sample mean minus the known population mean divided by the standard error. So that equals the same thing, the sample mean minus the population mean divided by the known population standard deviation divided by the square root of n. Now let's plug in our numbers. We know this is 1050 minus 1059 divided by 210 over the square root of 9. We know that 1050 minus 1059 is -9. We know the square root of 9 is 3, so we got -9 over 210 divided by 3. 210 divided by 3 is 70, so that equals -9 over 70. So our z statistic is -0.128574. Now, this formula should look very familiar to you. It's basically a Cohen's d in the hypothetical distribution. In the hypothetical distribution, our means are 0.128547 standard errors apart, and standard errors are just standard deviations in the random sampling distribution of mean differences. It's basically the same thing. And in this case, our estimate of signal is 0.128547, the size of your noise. And you're like, well, that's different from your Cohen's d, and you're like, of course it's different. Remember that the random sampling distribution of mean differences is assuming a normally shaped distribution. It's assuming the null hypothesis were true. It's assuming that the standard deviation of that distribution is standard error. So it's slightly different, but the idea is the same. And you're probably like, well, why do we calculate this? Well, we're calculating this because we need to convert our mean difference into a standardized mean difference, which is a z-score. That's what we're doing here on that random sampling distribution of mean differences if the null is true. So we're standardizing that mean difference so we can use tables that allow us to directly look up p-value, or so we can use computer programs that have the tables embedded in them so those computer programs can directly look up our p-value. So what I've done here, you'll notice I've added a z-score number line to our p-value problem and our random sampling distribution of mean differences. I've done that just to show you that, oh, like I've converted this mean difference of -9 to a standard z-score of -0.13, right? But mainly these two number lines are very similar. They have a limit of negative infinity, upper limit of positive infinity. The middle of the distribution is 0. The only thing that changes is I'm converting my mean difference and its mirror image into its z-score and its mirror image z-score. So now we have all the information in our problem, and we can go on and we can figure out how to solve for p. Step 6 is to simply solve for that p-value that we set up. Now, there are 3 separate ways that we can do this relief for. The first way we can do this is by using these paper tables where we can look up the p from the z-score. The second way we can do it is to use PSPP, which is the free version of SPSS. And of course, we can use SPSS. Now, there is a fourth way. You can go on the internet and find a Z to P calculator. That'll do it for you. But I'm going to discourage you from this option. It is easiest, I'm not going to lie. But I want to discourage you from it because the skills you are gaining in this class really are opening you up to some new careers if you pursue these statistical tools. Now, the first career you can pursue that's really interesting is market research. Now, imagine you worked for a company like Pepsi, and they wanted to test out new bottles, right? And they asked you to please run statistics on that, or to please run this experiment. Well, you can do that, and that's market research, right? You can figure out, oh, I'm going to show half my participants bottle A, half my participants bottle B, and have them spend actual money to buy the bottles right there in front of them, right? That's market research. If you want to be a market researcher, you need to start looking now for market research internships. But it is a really cool job. Outside of market research, there's a new kind of research called user experience research. Now, this is often centered around apps and how user-friendly they are. So UX researchers design studies that test how good an app is, or test our interfaces, like our interface with Netflix and how great that is compared to Amazon Prime or something like that. That's a really cool job. To get that, you need to also get an internship in market research. And then once you graduate, you want to get a boot camp degree in UX research. It's like a certificate. It's a certificate. So you want to get that. Or if you're really into this kind of stuff, you can be a data scientist, and they work for corporations on big data sets. They're the ones that are behind your Facebook page, creating the algorithms that are selling you things. Now, in order to do this, you definitely need an internship in market research. You also need a master's in stats, or a quicker way would be through a data science boot camp. They do have some data science programs at colleges, but the boot camps currently have better reputations because they offer this thing where if you do everything they say and you don't get a job, you don't have to pay for it. And if you do everything you say, you get an amazing job with an amazing salary that you pay them back for the education that changed your life. So I'm going to discourage you from going to the internet for the easy answer. I'm going to encourage you to use the programs that you will see in a second. You have this file. I'll change the name. It's currently just one I scanned to myself. And our problem is very simple. We found a z-score of 0.13, and we want to figure out what our p-value is. So I'm in my table and I'm looking for a z-score of 0.13, and I see two numbers, the percentage between the mean to z. So this is this area right here, that slice of the pizza, which isn't useful to me. So I'm just going to ignore this column pretty much every single time. And then I'm looking at the percentage in the tail. So the percentage in the tail is 44.83, and that's just in one tail. So the percentage so remember, percentage to probability is divided by 100, so that's 0.4483. So I know that when I go back to my slideshow, right, that here, I'm just going to pull this up real quick, that on my answer for these, I want to put 0.4483. Let me just double check that. My memory's going. Y'all know that. But what is it? 0.4483. I was correct. A good scientist always double checks when they're uncertain. 0.4483 here, 0.4483 there. 0.4483 times 2 is like 0.89. My p-value is 0.89. So I've just solved for p-value there. Okay, so how do we use PSPP to calculate our p-value for the z-test and some other things as well? So what we do is we have, like, there's no clicky box option to get a one sample z-test in SPSS or in PSPP. So in some ways, this is a more technical version of using SPS than you're probably used to. So one of the great things about SPSS is that it has these syntax, this syntax, syntax mode where you can literally type in SPSS commands like a computer and it'll run them. Well, what I have done is I have found a syntax that calculates the one sample z-test, and it's all self-contained. So all you have to do is you have to open up the PSPP syntax file or the SPSS syntax file on your computer. In this case, the PSPP syntax file on your computer. And what you have to do is you have to plug in the correct values for in this area right here. So the first thing, it says data list n. That's the first thing. N is 9. Sample mean. Well, my sample mean is 1059. My known population mean is 1050. And my standard deviation is 210. If you look here and you want to get into the math, you can figure out that it's doing everything we've talked about so far. So I'm just going to go ahead and run all of this right here. And what you see is a lot of stuff you don't need to worry about. It's just running commands. But at the end, the greatest part is you can see the exact values we had before for our z statistic. Our z statistic is 0.12857. Our p-value, if this is easier than using the table, right? Our p-value is given to us right there, 0.89770. And our Cohen's d is identical to what we had before, 0.0428. So this is beautiful. How do we calculate the one sample z in SPSS? The one thing I'm just going to tell you right now is there is no clicky box method for doing this. There is no way to do it with clicky boxes. SPSS has a very unique function in it where you can either do the clicky box method of calculating statistics, or you can create a new syntax window. Now, you don't have to create a syntax window, but syntax is just computer code for nerds, all right? So I wanted you to show there's all sorts of things you can do with the syntax window that you can't do with the clicky box method. One sample z is one of them, all right? And so I just looked online for SPSS syntax that calculates a one sample z, and I tested it to make sure it was doing it correctly. Now, right here, it says begin data, you have to enter your n in first. So that's your n. You have to enter in your sample mean, which was 1059. We have to enter in our population mean, our known population mean, which is 1050, and our known population standard deviation, which is 210. And if I just highlight all of this fun stuff and click run, what you see at the end here is it gives me this output that has my z statistic, my p-value, my Cohen's d, I was troubleshooting it earlier and I added mean difference and population standard deviation as well, but we plugged those in. So what you'll see in your syntax, I'll fix that up because I'll just take these two out right here and you'll just see these three numbers. But these are identical to the numbers that we calculated by hand. And it did it without any effort on my part, which is beautiful. So now we know how to use SPSS to get the one sample Z statistic, the p-value, which is what we're really after, 0.897. So let's just go over, I'll go over that p-value once we are in the slideshow again. But this is how you get your p-value. So we've calculated our p-value three different ways. We got 0.8970 all three times. And now we just put that on our problem. We're going to solve our p-value on our picture. I did it in this way where I just drew two arrows and said those both add to 0.8970. There's no reason to break it up into the two halves of whatever that works out to be. I don't even mind. But this, just put your p-value on your picture. You've solved your problem. You now know your p-value. All right, step 7, how do we interpret our p-value? Well, our p-value is tiny. The probability of sampling a mean difference has extreme or more extreme than the mean difference we sampled if the null were true is tiny, which we then take as evidence that we have disproven the null hypothesis statistically. I will consistently say we have disproven the null hypothesis statistically, but I know most other people don't. They will say we have rejected the null hypothesis, which is very similar to saying we've disproven the null hypothesis. The only reason we say reject is because we know there's a probability that when we reject the null hypothesis that we are incorrectly rejecting it. So if we have a p-value of 0.02, we're saying, yes, I believe statistically I've disproven the null hypothesis, but there's a 2% chance that I am wrong and that I'm making an error. There's a 2% chance of sampling a mean difference this extreme or more extreme if the null is true. So there's still a probability that I just got this mean difference by chance. But it's so small that I'm really just going to say, look, I've statistically rejected the null hypothesis. This is when folks use the word statistical significance. I myself am more inclined to use the word statistical difference because significance suggests that it's an important difference. You can have a p-value that's less than 0.05 that accompanies a Cohen's d that is tiny and meaningless and not even worth your time. When your p-value is greater than 0.05, you literally know nothing, and that's all you write. My p-value is greater than 0.05. I know nothing. Step 8 for me is you always need to make a graph. The APA manual says you don't always need a graph, but I want you to know what your graph should look like in case you want to use them. Making graphs is difficult, and you're going to learn more about this in lab. You're going to learn some of the basics. But what I'm asking you to do is a little bit more advanced than the basics. And instead of making you make your own Excel files, I'm giving you ones I've created to solve the problems for you. So all you have to do is plug and play your information. It creates your graphs. It also checks your z-scores and Cohen's d because there's nothing wrong with having double checks out there, double checking your answers. So right here we have our one sample z-test graph generator. I have already populated the graph for this practice example that we are discussing, and we already know that the p-value is massively high, and we can see in our traditional bar graph that those two means are basically the same. We can see that there for the means, but we also see a massive range in potential standard error. Those are standard error bars, so plus and minus 70 for this example. And, those are just your standard error bars, and they kind of tell you all the potential scores. So you have it where if you slide all the way up on one and all the way down on the other, you might have a massive effect. So, what we can see here, though, is that these two means are not different. And we also can see that estimate of those means are not very stable. Now, this bottom graph is a really cool graph. I would argue that the signal is the mean difference. And I've been arguing that all semester. Well, this mean difference is the most important thing in our entire study. So our 95% confidence interval is simply stating that we are 95% confident that the true population mean difference falls between a range of negative 146.2 and positive 128.2. And you're like, what does that mean? That means in the worst case scenario for me, because this is my SAT course, I am harming students' SAT scores by 150 points. I'm basically taking my classes, taking away 150 points on their SATs. That's the worst case scenario. However, the best case scenario is that my class is adding 128 points to their SAT scores. Just taking my class leads to a massive increase. So I am 95% confident that my program is doing one of these things, massively harming people, nothing, no difference, doing nothing, or massively helping them out. So in this case, you can see that the experiment's not really able to estimate the most important statistic, the mean difference. It tells me that I need to improve my experiment. I need to maybe change it up. So one of the ways to change up this study to make it better is we got to get rid of the individual differences here. We've got to, I would maybe do a totally different type of test, not these statistics, but I would do a pre-post test, doing a pre-SAT, then, some kids take my class, some kids don't, and then do a post-test after that, right? That's how I would examine that and make the study better, okay? But I clearly see that my study is not giving us a good estimate at all. It's real horrible. It's real bad. And so here it's telling me I know nothing. I know nothing at all. I don't know if there's no effect. I don't know if there's a good effect. I don't know if there's a bad effect. And that means if I don't know anything at the end of running a study, it means my study was done poorly. One of the things that was done poorly was my sample size. My sample size was 9. Let's see what happens when I increase that to a pretty good 90. What happens to my different graphs? Well, the top graph really didn't change that much. They're still not different from each other. In the bottom graph, you can see that we still don't have a great estimate, but we got a lot more precise. Right now, I'm seeing my effect is potentially a lot smaller. Worst case scenario, I'm taking 52 SAT score points away from them by attending my class. Best case scenario, I'm adding 34. And I want you to notice that Cohen's d is never going to change. That's also important as well. Now let's see what I do here when I'm saying we ran 9,000 people in our study. I want you to notice what changed the most. What drastically changed was this graph that's showing us basically our p-value. Our standard errors dropped down so much. And this difference that didn't matter at all now would be a significant difference. Our z-score, look, that change, that's a -4. That's a p less than 0.05 for sure. And our Cohen's d did not change. This difference is a meaning right now. If I ran 9,000 people, this difference is a meaningless difference. It doesn't really matter, but it looks significant. I mean, it would be significant, but it's a piddly little tiny difference. And my Cohen's d tells me that it's barely a difference at all. What else tells me that is my confidence interval. If you look at this worst case scenario, I'm taking 13 points from them. Best case scenario, I'm taking 4 from them. So I see that my program definitely hurts my students, but by something that doesn't matter at all, really. Taking 13 points away from them, taking 5 points away from them, that's really not, it's not important. But we might conclude it's important because what we notice is, as that interval got smaller, this p-value jumps to significant and it looks like it's meaningful. So let me see what happens when I make the difference between our sample mean and the known population mean as small as I can possibly think to make it. One SAT score. Can I make such a meaningless difference significant by increasing my N? Right? A 1 point difference on SAT score. Will that be significant if I go to 90,000? My z-score is 1.4, so it's not yet. What if I go to 900,000? Look at that. Look at this. With 900,000, this p-value is going to be massive. The z-score is again 4.5. Right? Got this massive z-score just by getting 9,000 participants in there. Now that's just on the lowest difference you can have, right? And you might be like, oh, that's a significant difference, but let's look at our 95% confidence interval of the mean difference, the very same data. Oh, worst case scenario, my program is taking away 1.5 SAT score points from them, which is nothing. Best case scenario for me, I'm only taking half a point away from them. This is a meaningless difference. Yes, there's some harm there, but it's meaningless. It's not important. Like, it really doesn't matter if I stop my program or keep it going. However, if you're just going on significant values, you think you found gold here. You haven't found gold. You found a mathematical difference that doesn't mean anything, that doesn't matter. So this is why we look at these graphs, so that we don't make those bad conclusions. Also, I just want to say, if you want to change anything, you just change the values in at the top. You can change titles, you can change everything. This stuff over here is calculating our 95% confidence interval. And it's using this formula where we take the mean difference plus or minus 1.96 times the standard error. And that just allows us to do the math to find the upper and lower limits. Those are the upper and lower limits of confidence for this specific point estimate. So, it's just that 95% confidence interval formula. It just allows us to find the middle 95% of a normal curve. So that's all it's doing. And we're translating that to upper and lower limits. But you don't have to understand that. You just have to be able to interpret these upper and lower limits in terms of worst case scenario and best case scenario for the researcher's hypothesis, the real one, not the null hypothesis. Our final step is to write our results as if we were going to publish it. My advice for everyone in here is to look up the most recent issue of the journal you want to publish in and look at how they present statistics or similar statistics to what you're presenting. So I did that. This is from the most recent edition of Psych Science, which is, in my opinion, the best journal out there. And, I just want y'all to see some stuff here. Look at, sometimes they report decimal points. Sometimes they don't, right? Percentages, people don't really report decimal points. For the p-value, nobody puts a 0 in front of the p-value because the highest the p-value can be is 1. And so we don't do that. But for Cohen's d, we put a 0 in front of it. And for a 95% confidence interval, we use these fun little brackets and commas, and we put zeros in front of it. So essentially, a lot of different people, a lot of different journals expect different things. There's some leeway in how you present it. What matters the most is that you get the numbers right. Now, I know you all have less leeway than I do when publishing, so I'm just going to acknowledge that. And I realize that you're writing for me and you're writing for another journal, the person who is teaching your lab course. I completely understand this. So, I'm going to be more lenient than they are, and that's okay. But I'm just showing you that there are some weird conventions in our field. Neuroscientists, you won't be writing an APA style. So now you know how to do statistics the right way. And it's time that you started. You're going to have to really look this up from journals in your field if you want to publish your research. Like particularly the folks that are doing like the fun EEG, EMG stuff, right? Like if you want to publish in a neuroscience journal, don't default to APA. Check out the journal, see how they publish stuff. I'm choosing a journal called Psychological Science that does use APA, but even there, it's not always clear, right? And I'm pointing this out with the p-value and the Cohen's d and all that. So essentially, here's my description of our results. A one-sampled z-test indicated that the average SAT scores of participants who received the SAT training course, I insert my means and standard deviation. I did not put in decimal places here because these numbers didn't have decimal places in them. And sometimes it's misleading to include decimal places. These were not statistically different. Notice I didn't use statistical significance. I used the word different. That's a Brian choice. I don't like the word statistically significant. That is my choice. You can use it. I do not mind if you replace statistically different with significant. I'm okay with that. I just will not personally use it on moral grounds. But I understand that you will have to use it in your papers for your lab, so please use it. But also, please allow me to not use it. And then I'm like, not statistically different from what? From the known population SAT average. Here I got this huge parentheses with a bunch of statistics. I have my population mean properly labeled, also no decimals. My standard deviation, sigma, properly labeled, also no decibels. My mean difference, I've included my mean difference. A lot of folks don't, but I've included it because I know that this is the foundation of the entire p-value problem that I am calculating. My z-score here, I've included a 0.13, but in psychology and in our journals, we don't put a 0 before our p-values. It's essentially because the highest p-value is 1, so, if you have a p-value of 1, you're likely not publishing it, at least traditionally in the field of psychology. And then I have C figure 1 in there because I made 2 figures. My next point, I kind of am drawing this out a little bit, but I'm saying the effect was small in magnitude. And my Cohen's d equals 0.04. I'm drawing this out because a lot of folks will still just look at the p-value, so I'm doing an extra step. I could have thrown that Cohen's d at the end of the previous parentheses, but I really want to make the case that this is a very tiny effect. And then I report my 95% confidence interval of the mean difference. Because I want to show how poorly this confidence interval is so that everyone knows that this study was not good. I didn't get a good estimate of the mean difference that I'm using to try to figure out if I've disproved my null hypothesis. But essentially what you can do for me is just copy this second bullet point and put your answers in for the example homework for your homework example that's on the next page. So I would like you to complete all the steps we have just talked about for a new problem that's similar. You created the SAT program, not me this time. So it's your SAT program. And you tested your SAT program on 5 students. You have a 1,200, a 1,500, 1,100, a 1,400, and a 0. I gave you some pretty easy numbers for your first one sample Z test. All the population mean and population standard deviation are the same as it was for my problem, okay? And this 0 score, you have a 0 score in there. I've double checked it. It's real. This kid really scored a 0, so it's not an impossible score. I don't know how this kid scored a 0, but they did. So now what you have to do is go through all the steps.